The next topic we're going to cover is going to be the interplay between generics and inheritance. So we're going to start with a quick reminder on polymorphism. So let's take an example. So we have here a variable sum object, which is meant to hold a reference to an object of class object. So we could put in this variable a reference to just about any object we have in our Java virtual machine. Okay, this is based on the fact that every class in the system inherits directly or indirectly from the class object. So in this case, we create actually an instance of the class object and we put its reference into some object. Then we have some integer, and we do pretty much the same thing here. Some integer is meant to hold reference to object of class integer. We create a new such object containing the value 10, and we assign its reference to some integer. And then this is a key to polymorphism, because an integer an object of class integer is from a class that inherits from the class object, then we have this is-a relationship. An integer conceptually is a type of object. So we can assign our reference some integer to the reference variable some object. Okay, this is a key to polymorphism. Now, integer is a number, the same way that integer is an object, right? So we could have a method named sum method that returns void, that takes a number n as parameter, so a reference to an object of class number. And we could call sum method with a new integer object or a new double object, simply because both the integer and double class inherit from number. So we have seen countless examples of this use of polymorphism so far. Now let's try to mix that in with generics. So we are going to use our box class example. So we have a box of number, box. So box is a reference variable meant to hold a reference to an object of class box of number. And we create such an object in the right-hand side of this assignment here. Okay, so new box of number. And then we try to use the add method from this box of number object. And we add first an integer and then a double. So our box is supposed to be able to store a reference to an object of class number. We pass a reference to an object of class integer, that would work. We pass a reference to an object of class double, that would work as well. No problem there. Well, it is an application with generics because box of number is a generic type, but really it's not really involving anything specific about generics and polymorphism. Okay, we have indeed a generic type box, but when we pass those parameters of type integer and double, please notice that the add method from the box of T class is not generic itself. Okay, that class accepts a data type. This data type has been set with a type parameter to be number. So from now on, the add method from the box of T class accepts a parameter of class number. Well, just like we've seen before in, again, countless examples, if you have a method that accepts a parameter of class number, like we have here in the middle of the slide, it can actually be passed reference to an integer object or reference to a double object. That's basic polymorphism. So even though we have a generic type here, we didn't do anything yet that forces this interaction between polymorphism and generic data types themselves. So that's exactly where we're going to be heading next. So let's consider the following example. So this time we have box test, okay, which is a method returns void. And it takes as parameter something that is actually involving generics. So instead of just taking as a parameter, for example, a number, which is a regular class, okay, this time we take a parameterized type, which is box of number. And this is where things are going to get much more interesting, okay? So the question that we have to address right now is, if we are trying to pass as parameter, as effective parameter, as argument, when we call this method an object of class box of integer, is it going to be accepted? Because the method says that the formal parameter should be a box of number. And intuitively, well, a box is a box, and well, let's say a number is a superclass of integer. So if we think about polymorphism, yes, that should fit right in. Okay. Same way, if we are trying to pass an effective parameter, an argument, also known as argument, when calling the box test method, and we make this argument of type box of double. Well, a box is a box, and a box of double should be a subclass of box of number, because double is a subclass of number. So if you are thinking about polymorphism when looking at this question, and you are basing your answer on every example that we've seen so far, most likely you're going to say, yes, these data types are suitable as arguments, okay? Unfortunately, this is where the trick is. The clue was misleading, leading you to think about polymorphism and draw some analogy was indeed the problem, because polymorphism is not going to work the same way here, because there are different rules about inheritance that apply. More specifically, a box of number cannot be seen as a superclass of box of integer or box of double. So we're going to dig into those rules right now. Okay, so given two concrete types A and B, like for example number and integer, we know the relation between them. So these are the concrete types that we use as type parameters. We know the inheritance relation between them, and this is what we used to reason about polymorphism in the past. Okay, now the rule that you have to absolutely memorize is that when you have a generic type like my class of A, then my class of A has absolutely no relationship whatsoever to my class of B. So you cannot have this diagram here on the right that would show, for example, that a box of integer is a subclass or is a type of box of number. That is simply not happening. That is forbidden. Okay? So if you were asking, well, what is the common parent, the superclass of my class of A and my class of B, then the answer is a little bit disappointing, because the superclass of those two is object. So if you took two completely unrelated classes, like a class employee and a class, I don't know, minivan, these classes may belong to inheritance hierarchy of their own, but they really have no relation whatsoever one with the other, okay? So if you were asking what is the common parent for those two classes, minivan and employee, you would come to the same conclusion, object, because every single class in a Java hierarchy inherits from object, the class object, directly or indirectly. So that's kind of the minimal common denominator, right? If classes have nothing in common, well, you can always say that they have object in common, and that's it. Okay, so the temptation is great here to assume that we can read more than what the syntax tells us, you know, that a box of number is a superclass for box integer. You need to be really careful. That is not actually correct. Okay, and we're going to delve a little bit more into this. Okay, so let's look at Java collection classes, because what the previous slide suggests is that as soon as you have, you know, a generic data type like box of, you know, something, then you cannot have any relation whatsoever between two different generic data type. And it's not entirely true, okay? As long as you do not vary the type argument between two generic data type, then you can have the inheritance relationship preserved. So let's look at an example here on the right hand of the slide. We have a collection of string, a list of string, and an array list of string. So these are three classes from the Java collection framework, okay? What they have in common is that each of them is parameterized with the same actual type parameter, string, okay? So there is an inheritance relationship between an array list of string, a list of string, and a collection of string, okay? And this is exactly the kind of relationship you would expect. What the previous slide was pointing out is that we could not actually have a type parameter that is replaced by one of its subclass and consider that the resulting, you know, generic types were somehow related by an inheritance relationship. Okay, so these are two different things. Make sure that you understand that, and if you have question, if that needs to be further disambiguated, jump into the forum and ask your question there, okay? This is really important you understand the difference between those cases here. So let's try to apply this and stretch it a little bit further, okay? So we are going to combine what we've seen here in those two last slides with actually trying to add additional type parameters to an interface that actually extends another interface. So our example is going to use the list of element interface, okay? That is from the Java collection framework as well. And we're going to write our own interface named payload list. And this one takes two type parameters, e, that is going to correspond to the e that we specify here for list, and p, okay, which is going to be a value. All right. So the method that we implement inside this interface, or actually the method that we require classes that implement our interface to provide code for, is set payload, which is going to take an index of data type, primitive data type int, and a value as second parameter that is of data type p. Okay, so a little bit more complicated than the previous example. Okay, the first example we had like a box of number, and then we're going to try to fit in, box of integer, box of double. The second example, we saw that if we have a list of number, for example, then we can have like an array list of number, and these are related by an inheritance relationship. Well, here we have two interfaces. We're going to look at their relation with one another, but the interface that we wrote actually extend list of e, but adds also another type parameter. So what is the impact of having additional type parameters in the rules that we have seen so far? Well, let's take a look. Let's take a look at the diagram here. So we are considering three different payload list generic types, okay? Payload list of string and string, payload list of string and integer, and payload list of string and then exception. So exception is a class, so we can very well, have this as object of class exception, passed as data type here. So what is the relation between those three different payload list interfaces? Well, they all extend actually the list of e interface. So as long as the type parameter e, which is string in this example, okay, we are talking about a list of string. As long as this type parameter e is kept the same when we define those data type here, payload list of string and string, the e was the first type parameter. As long as it's the same, we have this inheritance relationship. Okay, this is what we covered in our second example. So you can see that payload list of string and whatever is actually considered as a subclass of list of string, which is itself a subclass of collection of string, like we saw a few slides ago. All right. So if you have multiple parameters, as long as the one parameter that is used to represent this type parameter here and this one here is the same, then you can maintain this inheritance relationship as well. So at first glance, it's a little bit confusing, but spend the time thinking about those examples and ask as many questions as you need, because these rules are going to be what motivate us to seek different extension of generics, like for example, wildcards type parameter type instantiation, okay, which we are going to cover completely at the end of this module. But the idea is that to be able to appreciate what wildcards are going to do for us, you need to first appreciate what are the current limitations that you have to struggle with when you are trying to mix together inheritance and generic data types, or generic data types and polymorphism, since the two are linked together.